Missing jumps in games can feel very frustrating and unfair. To help with that, games employ several techniques to improve the feeling of fairness and input response, like Coyote Time, Blob shadows, and edge grabs. So let's take a look at those. In platformers that requires precise or fast jumping, it is very common that the player tries to jump just a few frames after the character starts falling, due to the reaction speeds or input delays. So a common technique used is called Coyote Time. This gives the player a grace period of time, usually a few frames, where they can still jump after falling. And the same is also true for trying to jump immediately after hitting the ground. Trying to press jump just after falling can lead to pressing it early or not registering the jump at all. Even trying button mashing the jump button can often lead to delayed jumps. So this technique also caches the user input for a few frames and allows the player to immediately jump when it reaches the ground. And to do that is fairly simple. So let's do that to our player controller here. I have here a simple third-person controller. It has some simple movement, a jump, and some extra code for the animations. Nothing too complicated. To add Coyote Time here, let's declare a Coyote Time variable of type int, which represents how many milliseconds the player can still jump after it starts falling. And we'll also create a last on floor to save the last time the player hit the ground. Now, inside our physics process, if the player is grounded, let's save the time with time.getTixMS. This returns how many milliseconds have passed since the game has started. But don't worry, this number will only overflow if you leave the game open for 500 million years. The next step is inside our jump. If the player is on the floor, or if the current time minus the saved last on floor time is less or equals than the Coyote time, it means we are within the grace period and can still jump. But that's a bit hard to read, so let's take this calculation and turn it into a function. We'll call this timeSince and accept the time we want to check, and return the current time minus the last time. Now we can replace it, and it is much more readable now. If the time since the last floor is less or equals than the Coyote time, we execute the jump. And now we can execute jumps after falling. Now, 200 might be a bit too much. Usually a few frames is already enough to make a difference, to make the player feel the game is fair. So let's set it to 50 milliseconds, about 3 frames at 60 FPS, which still works great. Next, let's buffer our jump input before landing. Declare a last jump input variable to save the time, and if you have pressed jump but have not jumped, let's save that time to the last jump input variable. Then, if we are on the floor, and the time since the last jump input is lesser than the Coyote time, we will still execute the jump. You can use a different Coyote time here for jumping or landing if you want more control, but using the same times here also works just fine for us. Now, there is still one problem left. Let's set the Coyote time to 500, just so we can see it easier. But if we button mash jump, the player jumps multiple times. That is, when the player is within the Coyote time, any jump is allowed. Not good. Because we have Coyote time now, we can't just check if the player is on the floor to allow jumps. So let's fix that by creating a hasJump variable. When the player is on the floor, we set the hasJump to true. And before we execute the jump, we first need to check if it can jump now, and set it to false after. But instead of repeating it here, let's instead do this check inside the jump function. So let's remove that, and change the name to tryExecuteJump instead. Then, on the jump function, we return if it doesn't have any jumps, and set hasJump to false, and jump otherwise. Now we can jump multiple times anymore. And the Coyote time is still working. Now, let's revert the Coyote time to 50, and check out another technique for precise jumping. When platforming in 3D, it is often very hard to know where the player is going to land. So a common technique used is Blob shadows. We put a circular shadow directly below the spot where the player is. And to do that in Godot is fairly simple. We just need to add a decal node inside the player. This node projects a texture and paints it over any meshes the yellow area hits. To make our blob texture, open the textures, and let's create a new gradient texture 2D for the albedo color. Inside the gradient, let's enable snap and position the origin point to the middle. Set the filter radial, and adjust the second point so it makes our blob. Then let's adjust the gradient color to be closer together. and change the white one to be black and with full transparency. You can adjust the fall off by changing the positions here. And let's also lower the transparency just a bit. Now, the decals by default modulate the opacity based on how far away they are within the area. But we don't really need that. So let's open the vertical fade and drag the fade curves all the way to the right, making the color consistent no matter the distance. Lastly, let's make sure the decal area is only below the player. And extend the lower part to whatever height you want your shadow to hit. Now, while this simple setup works, we have a problem. The blob shadows are drawn in every mesh it hits, including the ones below the platform, which is not very shadow-like. To fix that, we are going to need to change things a bit. Let's add a raycast to the player. We are going to use this raycast to position the decal area so it only affects one mesh, and the raycast target is going to be how far it reaches, so I'll set the Y to -10. Now let's call this node Blobcaster and put our decal node inside it. Let's reset the decal position and reduce the size just so it is easier to see. Then we'll create a very simple script for the raycast to control the decal node. Let's rename the decal to Blob decal and enable its unique name. Then drag it into the script, holding Ctrl before releasing it to create a variable. The script here is very simple. On the process function, if the raycast is colliding, we save the local lowest point with toLocal passing the collision point. This gives us a nice vector tree where the Y position is how far away the hit was. We can then use this to calculate the Y size the decal area needs to be, which is the absolute value of the lowest point .y plus a small value just so it intersects with the ground, and set the position.y to be the lowest point .y divided by 2, since the size increased from the center. Now our blob shadow works properly, not showing below platforms anymore. And if you go to the Remote tab and select the blob decal, we can really see what's happening. The orange decal area and the position are constantly changing to be the exact ones they need to be. Now we can execute high jumps and confidently land where we want, without having to guess anymore. And as an extra, let's also make a quick edge grab to give the player another chance. For that, let's create a new node and call it Grabber Pivot. Then we'll add a raycast and name it Grab Raycast. This raycast is what we are going to use to check if we can grab an edge. So, it is a small downward ray just in front of the player's head. And you can tune this later depending on how forgiving you want to be. But we also need another raycast. We are going to call this one Top Raycast. This ray is going up from the player's head top, and it is going to check if the player has space to jump up. So let's now create a script for the Grab Raycast. We'll make the Top Raycast a unique name and drag it as a variable, and also a reference for our player. Usually you want this inside your player scene, but since we already started on the main scene, let's just continue like this. I'll create an animating var to tell if the player is currently edge grabbing. And to detect the edge grab itself is very easy. We want the edge grab to be colliding, not currently animating, and the top raycast does not hit anything. And if the player Y velocity is 0 or less, meaning the player is either standing or falling, then we execute the animation and move the player. You can do this in several different ways. But because I don't have any grab animations, I'll just make the player jump up, then forwards. First, I set animating to true, I block my player's movement input, disable its physics process, and start playing my jump start, my placeholder animation. Here, often what is done is manually move the player's mesh, and when in position, re-enable the physics. But instead, I'll set the velocity up by 10, I'll wait 0.2 seconds to play the start of animation, then I'll re-enable the physics, which will unlock the velocity and propel the player up, wait another 0.2 seconds, just so we can clear the platform, and set its velocity forward by a bit with global basis.z. Then wait another 0.3 seconds before finally re-enable the player ability to move, and set animating to false. Now, while this feels complicated, the final result is really good. But we got one last problem. The Grabber Raycast is not following the player's direction. This is a common issue. What player controllers often do is rotate the mesh and not the player node itself. So unless the raycast is inside the mesh, the rotation will not work. Which is why we are going to use the grabber pivot. Let's take the reference for the pivot node and set its rotation to be the player's mesh rotation, which is the visual root variable in the case of this player controller. Now the grabber raycast follows the mesh rotation and we can grab away with no more problems, making our platform game feels much more responsive and precise. But that's it. As always, if you'd like to support me, you can get project files as well as other experiments by supporting me on Patreon. Now you can make responsive, precise platformers and improve your game's gameplay. I hope you like this video, and until next time.